Good morning. I'm James Friend from the University of California, San Diego, and I'm grateful for you listening to my talk. I'm going to be speaking on advancements in handheld nebulizers for pulmonary delivery. Most of the atomizers that we consider in our particular group have to make use of acoustic waves, and this is a relatively classic technique. However, many of the details are actually quite troublesome. The advantages of acoustic atomization include an ability to generate monodispersed droplets via an orifice-free or a clog-free scheme, as long as the different physical mechanisms can be harnessed. The classic view of acoustically driven atomization is that the mechanism is a parametric mechanism, or what's called a Faraday wave generation mechanism. At right is an example of a fluid interface where there are capillary waves appearing as a consequence of excitation. So Michael Faraday, back in the 1830s, discovered that if you shake a pie tin at a given frequency, lowercase f in the lower right-hand figure, then mercury sitting in the pie tin would actually show capillary waves that were one half that excitation frequency. In fact, he published a paper basically taking that pie tin with the mercury and tapping a chair that the pie tin was sitting on and watching the sunlight coming through a window. And those were the good old days when you could actually publish papers based on pie tins, mercury, and sunlight. But as it turns out, that it's a little more complicated than that. And in fact, over the years, that Faraday mechanism has been explored in quite good detail mathematically, and been used for a number of times to actually predict the droplet size. For example, in a seminal paper by Lang from 1962. So the issue is that while the math that has been used to make sense of this has been helpful, the problem is that the reality is rather different. When we look at excitation at the megahertz frequencies, instead of, say, physically tapping, we see far more complex phenomena. The video that's being shown here is a water droplet in air, and we're shooting at 900,000 frames per second. And you can see that it's not really capillary waves anymore. You have these droplet ejection events, and if you look closely, you'll notice sort of a bursting events off of the surface, and in fact out of the droplet jetting regime. This is 1 watt input power into the water droplet of about 1 millimeter in diameter, and it's at almost 7 megahertz. So this is actually what we see, and it in fact is a strongly nonlinear phenomena. And the traditional approaches of analysis that try to make sense of what Michael Faraday was seeing really have nothing whatsoever to do with the atomization process. And in fact, over the years, we've been busy making all sorts of devices to manipulate fluids in various ways, including atomization at the lower left, but also jetting, droplet transport, splitting film formation and transport. Pretty much, we discover new fluidic phenomena as a consequence of the very high frequency excitation that we use inside the system without a problem. But back to atomization, when we actually go through the trouble of exciting the fluid surface, say at 20 to 25 megahertz, for example, which is shown with a large peak, a very narrow peak at the right-hand side of this particular plot, what we see is that there is actually no Faraday waves at all. Again, we were expecting to see, if we excite the fluid at say 20 megahertz, that we would see a vibration appear at 10 megahertz in this displacement spectral density plot with respect to frequency. So there's an excitation, and there's no Faraday wave. And you'll notice, if you look at the upper right-hand side, the amplitude of motion is very, very small, but the acceleration is 9 million meters per second squared. And that's a feature of these high-frequency excitations. pardon me, which can give rise to a peculiar phenomena like we're reporting. Now, fascinatingly enough, we've shown over the years that with these large accelerations that it is safe to use large molecules, even cells, within these fluids, and they survive the process. The reason is because the excitation tends to be away from around 10 kilohertz to 100 kilohertz, which seems to be the range in which a lot of large biomolecules, and for that matter, cell membranes and organelles, exhibit resonant behaviors that can cause failure or denaturation of these molecules and cell membranes. All right, so what we see, though, in the excitation from 20 megahertz, instead of the Faraday wave, is actually a visible motion at a fundamental frequency of the entire droplet of around 200 hertz. And we see harmonics as well that appear, and these are physically separate harmonics, and you can actually predict these mathematically. But the problem of it is that as we increase the amplitude of vibration, you notice now that the acceleration is 60 million meters per second squared, that the modal character is completely lost. And this is actually a characteristic of a very strong nonlinearity. And so there are a lot of classical approaches to the analysis of these kinds of problems that become invalid. And so we've actually have a fair amount of funding now to actually look at this and the physics of this. But the key is to actually wonder why we get excitation at such high frequencies gives rise to a fundamental mode. It's sort of like taking a ping pong ball and bouncing it rapidly off a skyscraper and expecting the skyscraper to swing back and forth slowly. It's a rather bizarre phenomenon. But in any case, what the reason is that when you have the fluid droplet trapped on the surface, it forms an acoustic cavity. And so if you're designing some of these devices like with orifices or other things, then it is important to remember that you're forming an acoustic cavity where the acoustic wave will set up a standing wave in the system. And what happens is that this produces a pressure variation on the free fluidic surface, the fluid surface in contact with the air. That causes it to distort, and that changes then the shape of the acoustic pressure distribution of that standing wave within the droplet. That then causes a change in the shape yet again. And this occurs in hydrodynamic time, meaning slow time. And so the plot at the upper right-hand side is really what we're talking about here. And so this is actually the reason why we see the capillary waves form at such low frequencies. It's the attempt of the droplet to try to reshape itself to accommodate the presence of the acoustic pressure on the free fluid surface. And that happens slowly because of the fluid dynamics. Here's an example of one of these droplets viewed from the top during atomization, and you can see that slow vibration back and forth. Now this is 12,800 frames per second, so relatively slow compared to what we showed before. But the point is that the acoustic wave trapped inside of that droplet is being altered by the shape itself. Now, curiously enough, the distribution of the amplitude of the capillary wave that we saw before has discrepancies that appear. And those discrepancies appear when we see atomization. So, for example, isopropyl alcohol, triethylene glycol, and DI water, representing kind of a large range of fluid viscosities and properties. What we see are these humps or discrepancies that appear as a consequence of atomization. For example, we go from DI water that's green, and we see no such discrepancy. And then when we turn up the amplitude and start atomization, we see it. And so the reason for this appearing is it actually corresponds to the droplet generation rate, which is the first time this sort of thing has been seen. And what we can do is actually use this to predict the atomization onset and the rate of flow, depending on the fluid that is used to carry the drug that we might be wishing to work with. And so in any case, we can predict the atomization onset and then the rate of atomization, or the flow rate, that we might achieve as a consequence, depending on what we call an atomization Reynolds number, which is slightly different than the traditional hydrodynamic Reynolds number. So there's more here than the fluid dynamics. In fact, majority of the work that we've been successful with has actually been on the acoustic device itself. Traditionally, the nebulizer devices that are, for example, available for purchase for doctors' offices are relatively power hungry. They will consume 100 to as much as a kilowatt of power just to provide a medicated drug that you can inhale. And so therefore those always have to be plugged in, and they're fixed instruments that sit on the lab bench, and they're not very good at what they do, to be honest, because most patients report tasting the drug that they're consuming, and this is not unusual. And so we were wondering, well, what can we do better? Well, the first generation of the devices that we looked at, we used what are called surface acoustic waves that operate between 20 megahertz and, say, 200 megahertz. And they're relatively power hungry as well, about 3 to 5 watts of power. And they consume that, when they consume that much, it's very difficult to operate them off of batteries. And the ultimate vision here is to make it possible to make handheld nebulizers that a person could carry around, or in fact, plug into a phone and make use of in a discrete fashion in order to inhale a medication. So the first place to look is actually the piezoelectric material itself, and we defined a figure of merit here, sort of a estimation of the quality of the device, if you will. When we look at these different materials, PZT is lead zirconate titanate. It's a classic piezoelectric material. And then we also look at lithium niobate. Realistically, lithium niobate and PZT are the only two choices. There are other materials like langasite, which is very fragile, unfortunately. Barium orthophosphate, which is very expensive, and it also doesn't have anywhere near the performance of PZT or lithium niobate, and a variety of other choices that have a similar sort of issues. But when we look at PZT, we see that it's the traditional choice for these types of devices. Its figure of merit is actually quite a bit less than, say, lithium niobate, almost across the board. There are also different kinds of vibration behaviors that you can obtain. There's the thickness mode, which is a rather traditional type of approach, where essentially the entire material is vibrating in thickness. Means it gets thicker and thinner with the application of an oscillating electric field. And those have been around a good long time, although the lithium niobate versions of them are relatively new. Lamb waves are similar to the Rayleigh wave. There's really very little difference between them, although Lamb waves are entirely through the material, and a Rayleigh surface acoustic wave is on one face of the material. Now, one of the things that one finds is that Lamb and Rayleigh SAW have relatively low figures of merit as well compared to the thickness mode. The reason is that the entire material participates in transducing the electric signal to a mechanical stress and therefore vibration in the thickness mode. And they do so, it does so in concert. With the Lamb wave and Rayleigh wave, there's a lot of motion that's induced that actually does nothing to produce the useful vibration needed to perform atomization. When we look at the figure of merit results finally, we find that the 128 degree lithium niobate cut is actually the best material to choose here. And traditionally, a 36 degree lithium niobate cut is thought to be the best for thickness mode. That's true for non-resonant applications. For resonant applications, actually turns out that the 128 degree cut is the best material. So, in any case, you can actually plot the figure of merit versus the substrate displacement versus the figure of merit. And you find that with the PZT, it's at the lower left, so it's relatively poor. The Lamb and Rayleigh SAW materials are kind of in an intermediate range, and then the lithium niobate thickness mode devices are arguably the best. So as a consequence of this, this is our first lithium niobate based thickness mode device, and it's completely battery powered and handheld, as you can see here. This is a relatively crude device, but working in a university environment, the whole point of this is actually to show the prototypes working rather than to show a final product that would need quite a bit more work and validation and adherence to ISO IEC standards and all of that. And so in any case, what we're showing here is ability to generate atomization from just standard water, about 0.5 milliliter a minute, which is okay for modest inhalation purposes. This works with a variety of fluids all the way out to octanol, which is a very viscous fluid. In this particular case with water, it's generating 3 micron droplets. And most notably, its power consumption is about 750 milliwatts. And so, relatively speaking, it's relatively low power. And it's something you can run off of a battery or, for that matter, a mobile phone. This is another example. In this case, actually, we're showing high flow rates. This is 2 milliliters per minute at 1.4 watts. And it's producing 3 micron droplets of water. This is actually the greatest atomization flow rate that's ever been demonstrated for per unit power, and so we have essentially a very high flow rate that's suitable for for example, for rapid inhalation purposes or inhalation on demand, 1 or 2 puffs, and produces this massive flow rate. This is generating a monodispersed droplet size. So the range of droplet sizes here is between about 1 micron to about 5 microns. So what we've seen is essentially a 2-order magnitude increase in atomization efficiency from going from a surface acoustic wave device as a classic approach now to using, say, a Lamb wave device, which it turns out to be slightly less efficient than a surface acoustic wave device. And you could use a mixed mode type of device that turns out to as well be not nearly as efficient as a surface acoustic wave device. And then we have a thickness mode device, so we just has shown that's on the order of 1 order greater efficiency. And now we have the handheld device with an optimal thickness mode design that is yet another order of magnitude more efficient again. And we're putting in about 1.4 watts, which is at the higher end of what's suitable for, say, battery operation. But on the other hand, it's generating 2 milliliters per minute of atomization for water. So, as you all know, it really matters in the context of drug delivery, and of course that's why we're all here at this particular meeting. And my way of thinking that the reason that I started on this work was because of the aim to try to find an alternative to injection, which we're all too aware of now as being a vital way to, say, deliver vaccines. But there's a lot of other things that you can deliver with injection that potentially you could deliver with inhalation. And as you know, it's an infection-free route to the cardiovasculature, painless and convenient, and it's better efficacy and safety compared to systemic therapy for diseases that primarily affect the lung. The lung is a very common route for viruses, and I think it remains an open question as to whether the delivery of medications and then, for that matter, vaccinations via the lungs might be effective as a consequence. You might say, well, that vaccination via the lung is impractical given the tight junctions and a variety of other issues. But there's a published literature that is showing that it is actually becoming possible to do without those issues being a concern any longer. Of course, the average cost of developing a drug, and these numbers are a bit old. 800 million, it's almost double that now. And the average time to market to a drug is 9 to 14 years, and just in time for your patents to expire. And pulmonary delivery adds 3 years and on the average of 300 million to that number, and so it's a bit of an issue. However, with a nebulization, potentially you could skip some of that challenge with the dry particle or the MDI inhaler approach, where you have to develop those dry particulates. You can actually deliver the original medicament and skip the dry aspects of it with the stability issues potentially. So that's our motivation, really, to try to look at the lower respiratory infections, COPD, lung cancer, asthma, and then obviously, and this, believe it or not, this slide is relatively old. It dates from a few years ago, and so viral pandemics and outbreaks. Wouldn't it be great if we were able to avoid having to have needles to deliver these vaccine injections? So I'd like to thank you for your time. And I wish to thank Polytech Irvine and Optech Laser in Belgium for the support of the work that we're doing, and funding from ONR, Keck Foundation, NIH, NSF, American Heart Association, and Department of Energy, and all my students and postdocs and team for all the hard work that they do in making these things happen. Thank you.